Dear all, thanks for the kind introduction from Professor Zheng Cruz. My name is Zheng from Dongguan University of Technology. Good morning, good afternoon, good evening for everyone, because we have from the different time zones. The topic of today is my great honor to make a presentation in the IIFC webinar. The topic of my presentation is related to the design and construction practice and some design methodology to the research on this field, how to use the FRP reinforced seawater and sea sand self-compacting concrete structures. My name is Zheng. This research is carried out by the several group staff in my group member, including Dr. Li Fei Zhang, and Dr. Lin Zhuzhou, and Dr. Bodi, and Dr. Ren Yuanqing, and Dr. Miss Yang Bixuan. And furthermore, this also includes some collaboration research between my research group and the research group led by Professor Susan Taylor from Queen's University of Belfast. This is the outline of my presentation. I will introduce some research background and then the bond behavior, the fractional and shear punching behavior, and finally we will discuss some time-dependent behavior of the FRP reinforced those SWSS-SCC structures. And finally, we'll try to present some construction practice using those novel materials. First one, we want to make an introduction of the research background of this, because most of the colleagues in this webinar is research on the composite materials. Has been well reported. The sustainability of the infrastructures in all over the world is due to the steel corrosion and some high carbon dioxide emission in the produce of the cements or some concrete materials. And furthermore, in current stage, in the current large construction in China, the river sand is not allowed to be used due to some environmental protection factors. Therefore, the engineers and the academics are seeking some solution to how to solve those and avoid those problems and status. Therefore, we try to use the FRP reinforced self-compacting concrete using the seawater and sea sand. As well, it's evident that the corrosion of the steel reinforcement inside concrete has caused some serious safety, social, and economic problems. In China, we can find that a 2.8 trillion economic loss, RMB lost, is caused by steel corrosion is around 3.3% of the GDP in 2018. Therefore, how to solve that? Maybe you can use some brokerage construction material to replace the steel rebar. We can find that if we use the fiber reinforced polymer reinforcing materials, that could be an effective way to solve this problem, to solve the problem of some short surface life, low safety and reliability, and weak disaster prevention or mitigation ability, and high safety and durability requirement can be obtained. And furthermore, those materials have some lightweight, high strength, corrosion resistance, and convenient for the construction, and effective to improve the structure before performance. This reinforcing material can be widely used in some marine engineering, bridge engineering, or some underground engineering. And furthermore, why we want to provide some research related to the self-compacting concrete, because this is a collaboration between my research group and Susan Taylor's research group in Queen's University. We can find that if we use the fly ash to replace the cement, try to produce the high volume fly ash self-compacting concrete, we can compare to the traditional concrete is uniform filling, and then the fill bubbles, the voids, and the reduced initial damage and enhance the durability of the concrete. And therefore, when we extend this research, try to combine the seawater and sea sand with those high volume fly ash or high volume industry byproducts self-compacting concrete, we can find that the concrete made with the seawater and sea sand develop some earlier strength faster than ordinary concrete, and the long-term strength compatible to the ordinary concrete. Furthermore, the durability issues can be effectively addressed through the reinforcement of the FRP. and then use the seawater and sea sand can help to reduce the demands of the fly ash resource and the river sand. And furthermore, we also reduce the transportation costs. And finally, the behavior of the seawater and sea sand self-compacting concrete compared to the traditional self-compacting concrete, the behavior is better than that. Therefore, we try to combine those materials together to produce. Therefore, it has been evident that we use the FRP as the replacement of the steel reinforcement is an effective way to solve the steel reinforcement corrosion. And therefore, based on the FRP material properties, the seawater sea sand can be used in the concrete production. On the other hand, some environmental friendly concrete can be adopted by using the high volume industry product such as fly ash, but as a replacement of cement, we can produce the self-compacting concrete. Additionally, our research will combine those materials together. We try to use the FRP as a reinforcing material and use the seawater and sea sand self-compacting as the for construction. Therefore, we can find that it can reduce 3 problems, including the steel reinforcement and the low carbon dioxide emission, and then reduce the use of the river sand and the fresh water. Those problems can be solved together. Therefore, in this research, we develop a comprehensive study, including the material research, the mechanical properties, and the component development and the construction practice. The second part of this presentation is where we try to introduce the study of the bond behavior, the tensile stiffening behavior of the FRP reinforced SWSS-SCC. In the first stage of the study, we used the pull-out test to study the bond behavior between the concrete, the bond behavior between the reinforcing material and the concrete. And additionally, we also used the AE method, the acoustic emission method, and the piezoceramic as the transducer to identify the damage process of the whole the bond test. It can be seen in those figures compared to the steel reinforcement, the bond strength will be lower due to the lower elastic modulus, and the bond stiffness also can be reduced due to use the FRP reinforcement, and some damage can be found after we remove the concrete. And compared with two concrete, use the self-compacting concrete and the normal concrete, due to the better compactness of the self-compacting concrete, we can find the higher bond strength in the FRP reinforced seawater and sea sand self-compacting concrete. And in those behavior, those results can be expected. This is the comparison of the influence of the steel reinforcing material, including the steel and FRP. Well, furthermore, we also use some PP fiber inside the concrete. We can find we were increasing some PP fiber inside the concrete, the bond behavior can be improved. And furthermore, with the increasing the development length, the bond strength also can be increased at the same time. And furthermore, we can find that when we use the different model, the seawater and sea sand self-compacting model, we can obtain the better higher bond strength due to the better compactness between the concrete and the FRP reinforcement. And finally, we get some result. The type of concrete has a little effect on the bond strength between the FRP and concrete, but use the self-compacting concrete can improve the bond strength a bit. And the bond strength was decreased with the increasing of the reinforcement diameter. That has been reported widely. And the bond strength of FRP reinforced seawater and sea sand self-compacting basement is compatible to the steel reinforced as seawater and sea sand self-compacting basements. And the increase of the lip height in the reinforcement has resulted in a significant improvement of the bond strength. And the second part of this stage, we use the piezoceramic to try to identify the hold failure modes of these bones of the bone slip, and try to quantify the damage level of the bone failure. That can be found with this is at the beginning of the bone test, and this is with the pull-out test. The signal that can be found, it will change significantly. And after that, we use the wave-length energy ratio to establish the indexed to quantify the damage in the bone failure. And we can find that it shows a good correlation with the test result. Therefore, we can use that to quantify the damage level or the bone behavior or the damage in the bone behavior of the FRP and the self-compacting concrete. And the third part of this study, we try to use the AE method, is the acoustic emission method, try to identify the initial damage location in the bone test. We use that can be identify the initial damage accurately. It's in the part close to the load applied. And furthermore, we also can use the method to identify the failure modes. We can find that for the FRP reinforced specimen, the failure mode is determined by the friction is dominated. But for the steel one, is friction combined with the mechanical interlock. Is based the signals from the AE methods. And the third part of the bone behavior we study, we try to use the current prediction method, try to predict the bone strength and the embedment length for the FRP reinforced seawater and sea-sand self-compacting concrete. In this comparison, we can find that the effect of the reinforcement diameter is overestimated, but the effect of the concrete interface compactness has not been considered. And therefore, we try to consider the small aggregate inside the self-compacting concrete, try to establish the accurate prediction for the FRP reinforced seawater and sea-sand self-compacting concrete by developing the length for the prediction method for the bone strength prediction. And furthermore, we can use that to predict the development length to use the FRP and self-compacting concrete in the future. We use the current prediction method for the bone slip curves. We can find that modify the BEP model show the accurate results to predict the bone slip behavior for the self-compacting concrete and the FRP reinforced structures. And therefore, we try to extend further research, use the artificial inertial networks methods to use to predict the bone strength with the following input factor, including the bar diameter, the tensile strength of the bar, the elastic modulus of the bar, and the concrete compression strength, and the thickness of the concrete cover, and the embedment length. The total allowed 560 experimental data will be collected to establish the database. We can use the method. And finally, we can use the method. So it's the prediction of accuracy of the various formulas, including the current design standards and some models in some reported literature will be used. We can find that the existing formula predict the bone strength the accuracy is not very good. But use the AN method, we can predict the bone strength with higher accuracy significantly. And the second stage of this study, we try to extend this research to study the composite behavior or the tension stiffening behavior of the FRP reinforced self-compacting concrete. We can find that we try to investigate the composite strength. It can be expressed by this formula. We try to study the composite strength and compare with the strength of the FRP bars. We try to study that and try to investigate the cracking behavior of these specimens, the direct axial, the specimens subjected to direct axial forces. And this is the second stage will be investigated in the whole test process before the cracking appear and the cracking development. This is the failure mode in our study. We can find that the effect of the reinforcement ratio has a strong effect on the tension stiffening. And we can find that when we increase the reinforcement ratio, the energy contributed by the concrete will be increased significantly. And then finally, we try to use the current design method, including the MC78 and the Eurocode and the ACI method to compare with. We can find that the Eurocode showed a better prediction compared with the test result. Finally, in this stage, we get some conclusions that the self-compacting concrete improved the bone behavior and in bone, the damage mechanism can be identified using the piezoseismic transducer, and the local damage location can be identified using the AE method, and the AAM method can be accurately predict the bone strength in a database with a lot of specimens. And the formulas calculating the bone strength and college length for the FRP reinforced self-compacting concrete is proposed. And the further study, we will try to study the long-term behavior of the FRP and seawater and sea sand self-compacting concrete. The third part of this study, we try to investigate the fractional behavior, especially the serviceability of FRP reinforced seawater and sea sand self-compacting concrete. We use some one-weight slab strips to develop this study. BFRP and GFRP also was used in this study. We use two types of material. We try to investigate some reinforcement ratio, and then we try to study the types of material and the reinforcing materials. And in this material, we can compare the fractional behavior. We can find that the failure modes of the fractional components. This is the typical failure mode for the FRP reinforced concrete slab. The shear compression failure can be found obviously. This is due to the low transverse shear stiffness of FRP reinforcement. And this is typical, the pure fractional failure can be found in the steel reinforced FRP. But in those figures, we also can be found that the relationship between the maximum cracking spacing and the average cracking spacing is almost linear. And furthermore, the relationship between the maximum cracking spacing and the average cracking spacing is around 1.385. That means this behavior also can be used some design codes or some prediction methods for the steel reinforced concrete structure also can be used. But we developed the cracking wise, we can find that the change of the materials, concrete materials have not a strong effect on the crack wise, but we're increasing some PP fibers inside the concrete matrix that can be reduced the maximum crack wise. And the reinforcement and the reinforcing materials have a strong effect on the crack behavior. And when we're increasing the reinforcement percentage, increasing the FRP reinforcement percentage has resulted into the smaller crack space. Those can be expected accurate. And furthermore, we can find that also can be found that the maximum crack wise and the average crack wise, we can find that a linear behavior can be found in the FRP reinforced self-compacting concrete. But for the steel reinforced one, the turning point was found in this behavior. That means is attributed to the stronger compatibility between the FRP and the self-compacting concrete. For the deflection behavior, those results the influence factor can be expected. They will not be discussed here. In this stage, we try to establish a governing factor for the structure design for the service limiting state. We established three factors. The first one is the stress on the material limitation is included for the concrete compressive strength. Furthermore, it's the crack-wise limitation, and the deflection limitation is limited to be these limited values. And then the maximum crack-wise was limited to the 1.5 to 1.7 millimeter. In this study, we can get a conclusion that for those studies, we can find that the surface load for each the service limited state in the FRP reinforced self-compacting concrete is related to the ultimate loads to the cracking load for the comparison purpose. The crack wise can be used for the design for the service behavior. But for the load and deflection response, we can find the current design standard is also most of the current design method show a good correlation with the test result, especially the model provided by Professor Ben Morcram. Furthermore, we also extend the research to the crack spacing. For the maximum spacing, we use the Euro code and the model code 19. We can find the Euro code show the better prediction. Those two models have shown a good prediction to predicting the maximum cracking spacing. But for the average cracking spacing, the bone coefficient need to be modified. After the modification, we can find that we can use the Eurocode to have a good prediction to predict the average crack spacing. But the JC, the Japanese code, cannot predict the accurate prediction. But finally, we try to investigate the maximum crack width. But in this study, unfortunately, we can find that the prediction from the current design standard and some results in some literature show the accuracy cannot be acceptable, and the prediction is quite scattered. And therefore, we also establish prediction method to predict the maximum crack width. And this result have the details for this prediction method have been reported in my published journal. And we can find that in our proposed crack width show a good agreement with the test result for the FRP reinforced seawater and sea sand set compacting concrete. And finally, get some conclusion for some surface behavior. And the surface behavior is for this seawater and sea sand set compacting concrete is quite similar to the conventional vibrating concrete. And varying the axial stiffness of the reinforcement have a strong effect for the serviceability. And the most restricted for the service limiting state is the crack width at the surface. And the current, we can find that the bond coefficient need to be modified to predicting the average crack spacing, and the accuracy of the maximum crack width prediction have been proposed by this research. Those was affected by the reinforcement percentage. For the further study in this stage, we will extend to the stage for the long-term deformation for the FRP reinforced the seawater and sea sand set compacting concrete. The fourth part of our study is also the focus of my research is the shear behavior, especially the shear behavior of FRP reinforced the seawater and sea sand set compacting concrete structure. We developed a quite comprehensive experimental study that will not be discussed here, including the GFRP reinforced the concrete beams, the hybrid FRP, GFRP, and CFRP, and the FRP grid. We published several papers to investigate the size effect, the arc effect in the deep beams, and the shear contribution from the steel roughs. And those has been reported widely. The significant disparities in the shear performance between the FRP reinforced the concretes and the steel reinforced concretes. This is due to the lower stiff elastic modulus and low linear elastic material, and the bend joint, the fiber, the wrinkling. That will cause no stress distribution and relatively small downward action and the reduced tensile strength of RP in the bend joint and increase in the width and the height and the diagonal cracks. But in our current design method, we can find that the total shear capacity for the FRP reinforced concrete is commonly determined by the the combination of the shear contribution from the concrete and from the steel roughs. However, we can find that the current design standards for the shear capacity prediction method, the great variation in the wide range among the different models lacks of the consideration of the size effect and the arc effect. And the constant value for the effective strength will be used to predict the contribution of the FRP steel roughs. But at the first stage of this study, we try to modify the prediction for the contribution of the prediction method for the contribution from the concrete. We also use the current design methods. We can find that the size effect and the arc effect that has been considered for several codes, including the CSA model and the ACI codes. But for the CSA model, the influence of the shear reinforcement on the size effect has not been conclusively determined. And furthermore, the research on the beams of the arc effect is insufficient. It's leading some high underestimation of the arc effect action in the various design codes. And in those methods, we can find that the factors have been investigated fully in my study, and the size effect have been considered in those three models, and the arc action have been considered in the CSA model. Therefore, we established a database, including our own experimental works, to establish data. The first database is the model without the steel roughs. This is the variation, the distribution of some of the model in our database, including the surrender ratio and the effective depths. For this database, we carry out a Pearson correlation study. We can find that the strong positive correlation is detected between the effective depth and the shear capacity. That indicating that the effective depth increase, the shear capacity increase too. And furthermore, the same effect we can find that for the shear span ratio. The ratio between the shear span to the effective depth has a strong positive correlation with the shear capacity. Therefore, we can use those current design standard to predict the test result in our database. We can find that the errors can be found significantly in the model with the small shear span ratio, especially for the span ratio smaller than the 2.5. And we can find that compared to the other design codes, the CSA model show a higher prediction accuracy due to the size effect and the arc action have been considered in those models. And therefore, we developed some statistical analysis that due to this quite complicated, we will not be discussed here. Therefore, based on the statistical analysis, we try to develop some modification for the CSA model. We develop several numerical models to investigate the influence for the shear span ratio on the shear capacity. But how we can find that is this value, the 2.5, should be modified to be 3 after the shear span ratio if the shear span ratio less than 3 is less than 3, the normal shear strength decrease with the increase for this ratio significantly can be found in this figure. But if with the shear span ratio larger than 3, the normal shear strength has to be stabilized. That means this limit value could be found that the inference could be determined to be the influence factor for the arc accent inside the concrete beams. And furthermore, we also developed a study for the size effect inside the concrete beam. This is our test results. We can find that the size effect still very dominant. It's very dominant in the FRP reinforced seawater and self compacting concrete. Based on those two observations in the test and the analysis, we can try to modify the CSA model. Include first one, the size effect should be considered in the whole process, and no matter even though the steel rod ratio is larger than the minimum steel rod ratio values. And furthermore, the 2.5 the limit value should be modified to be 3, and the size effect should be considered even though the effective depth of the concrete beam is larger than 300 millimeters. After this correct modification, we can find that the accuracy can be improved significantly. Therefore, we can use this model to predict the contribution of the concrete, the self-compacting concrete, to the shear capacity. And second part of this study, we try to establish an accurate prediction method for the prediction of the shear capacity contribution from the FRP steel rods. We also use the current design standard, try to develop some investigation. We can find that the investigation of the effective strength for the FRP reinforcement of FRP steel rod in the FRP reinforcement is necessary. But in the current design standard, the constant will be used. But in the FICO's study, it recommends the strength limits for the steel rod need to be modified according to the materials of the FRP. Therefore, we establish a database with the FRP steel rod and without the FRP steel rod. We establish this database including the 81 samples. We use this model, the total shear capacity minus the model without the FRP steel rod to obtain the contribution of the shear capacity contribution from the FRP steel rod. We use that to try to study the average strength of the FRP steel rod at the ultimate state can be investigated based on this database. Therefore, we can use test result to compare to the current design standard. We can find that only the JSC model use a function to predict the effective strength for the FRP steel rod. However, the prediction, the accuracy is quite low. It just consider the influence factor has not been considered by this model accurately. And furthermore, we can find that if you know the CSA model and the ACI model use the constant value, the prediction is the accuracy cannot be acceptable. The influence of the structural variables on the strain limits for the FRP stirrer need to be studied further. In the beginning stage, we can find that this is with the changing of the FRP material for the FRP stirrer. We can find that at the ultimate state capacity, the average strength of the FRP stirrer is not a constant, and the average strength of the FRP stirrer is closely related to the several design diameters. And the current design commonly underestimated the average strength of the FRP stirrups. Those will be changed by the FRP materials. Therefore, we also develop a Pearson analysis for this method. We can find that the concrete strength, the effective depth, the longitude reinforcement percentage, and the elastic modulus of the longitude FRP bars, and the stress band ratio, and effective strength has a positive correlation. And furthermore, the ratio of the FRP stirrup and then the material elastic modulus of FRP stirrup exhibited a negative correlation. We use that to develop a statistical analysis. We establish after some regression analysis, we establish a function to predict the effective strength for the FRP stirrups. And furthermore, for the safety consideration, it's recommended a dual control approach based on the strain limits for the shear reinforcement and the strain at the bend joint for the FF stirrup. The two-way control approach will be used. And use this method, we can find that compared to the current design standard, the effective strength of the FRP stirrup can be predicted accurately. Use our method. After that, we combine those methods together. The contribution from the concrete and from the stirrup, we use that. We can find that after the comparison with some and the third database for the correlation, we can find that our proposed model show the better correlation, the prediction results. After we get some conclusion, the existing codes did not consider the arc action and the size effect fully. And the FRP stirrup work less effectively to avoid the size effect. The size effect cannot be suppressed completely by using some FRP stirrup. The size effect still need to be considered, even though the FRP stirrup is used for the construction. And the strength of FRP stirrup closely related to the several structure parameters, such as the beam depth and then the concrete strength and the stirrup stiffness. And the current practice design standard using the constant value is not reasonable. And our proposed model show a good correlation with the test result. And further study in this part, we want to use some novel structural health monitoring, try to investigate the shear failure mechanism. And furthermore, we want to use some construction-friendly materials because for the FRP stirrup, this is not construction-friendly production. We try to use some FRP mesh, some soft FRP mesh to replace the FRP stirrup as the FRP reinforcement material in our for the FRP reinforcing concrete structures in the future. This is our further study. And the fifth part in my presentation is the punching behavior of the FRP reinforced self-compacting concrete structures. Our study will be focused for the concrete bridge deck slabs. Because for the punching failure is the common failure for the bridge deck slabs. And furthermore, due to the existing of the external restraint stiffness, the action have a strong effect on those material, on the structural behavior. This is the structural variables in our study. We try to investigate some reinforcement ratio, the type of concrete, and the reinforcing material. Those the test specimens preparation in my study. In the test result, we can find that the punching behavior is dominant in all the specimens. But if we use some PB fiber inside the self-compacting concrete, the failure will be not so brittle compared to the model without the PB fibers. And then furthermore, we try to investigate the punching angle because we found that smaller punching angles means the larger contact areas between the concrete. And then that we can find that if we're use this more circle method, we can find that if we're increasing the horizontal restraint, the punching angle could be reduced. That means higher punching capacity can be obtained. We also use that to predict it, and can find that due to in this method, the restraint stiffness is fixed. The punching angle is also fixed too. We also developed some study the cracking behavior with the ultimate strength, and is expected that the bilinear behavior can be found for those deck specimens. And the focus of this study, we try to establish the punching capacity prediction method with the consideration of the arching action inside these concrete bridge deck slabs. We used the model with some cooperation with Queen's University of Belfast. We used a model our joint published paper in ACI structural journals. This is the prediction procedure. Because existing the arching action, the compression zone the height of compression zone can be increased compared to the bending prediction series. We use that this model is for the steel reinforced concrete bridge deck slabs. Therefore, we use this method we also consider the flexural punching behavior and the shear punching behavior also have been considered in this prediction. And furthermore, the first part, we also try to establish the effective wise with the considered arching action inside the concrete, and also need to quantify the external restraint stiffness. These models, the first two parts of this prediction, and this model also can be found in this journal paper. And in our study, the focus is due to the increasing of the height of the compression zone inside the concrete. The effective stress level of the FRP reinforcement inside the bridge decks need to be predicted accurately. Therefore, we propose an integration method to predict the effective stress level inside the concrete bridge decks. We can use that to predict it. And furthermore, we also predict a modification to predict the shear punching capacity with the consideration of the difference between the FRP reinforcement and the steel reinforcement. And those methods also have been published in our paper in the engineering structures. And after that, we can compare our test result with some current design standard and some punching prediction model in some published paper. This is our model. We can find that our model show better agreements with the test results. And after that, we extend this research to use also establish a database for the current from the literature from the reported literature. We can find that the current prediction method, the accuracy is not good. We can furthermore the reliability is not good too. But if we use our method, we can use for this database. Our model can predict the punching capacity for the FRP reinforced bridge deck slabs accurately. And finally, with some conclusion is the experimental and theoretical investigation found that the FRP reinforced self-compacting concrete show a similar behavior of the normal concrete structure, bridge deck slabs. And the reinforcement ratio has little effect of the bearing capacity of the bridge deck due to existing of arching action or compression membrane action. And the current design standard is quite conservative. And then we can use our proposed models show a good correlation with the test results. The further study for this part, we extend to some construction practice. And the final part for some investigation in this part is the time-dependent behavior of the FRP reinforced seawater and sea sand self-compacting concrete structure. We developed some study for the shrinkage and the clip for this novel concrete material and the time-dependent behavior of the interface and the long-term deformation for this GFRP reinforced seawater and sea sand concrete beams. And with the first part, we try to investigate the shrinkage for total shrinkage, including the autogeneous and the dry shrinkage for these concrete materials. We can find in these figures when the other parameters are the same, due to the seawater and sea sand was used in this study, when we're increasing the chloride ions, it played a certain role to reduce reducing the dry shrinkage, increasing the autogeneous shrinkage for this seawater and sea sand concrete. And furthermore, when we're increasing the fly ash, the similar situation can be found. The fly ash, increasing the fly ash replacement the cement, it could be reduced the autogeneous shrinkage, but it will be increased the drying shrinkage for the seawater and sea sand self-compacting concrete. Those methods also can be. The microscopic photos also show that the larger flash content and the more loose the concrete microstructures, and the more porous contents and the numbers of the larger pores will increase too. And furthermore, when we're increasing the curing temperature for the seawater and sea sand self-compacting concrete, it can be increased the second hydration of the fly ash and speed up the hydration process. Therefore, the autogeneous of the shrinking strength is increased. And furthermore, when we at the same time the shrinkage of the specimen at the high temperature curing into the stable strength period of the 20 days earlier than that of the ordinary specimens. And the second part for this concrete material, we'll try to study the clip behavior of these concrete materials. It can be found the current design codes cannot be used directly for this seawater and sea sand self-compacting concrete. The prediction formula need to be modified with some consideration of the coefficient in the view of the correlation of the coefficient of the increase the concrete strength and the environmental related humidity has a strong influence on those test results. Among them, the modified parameters were obtained to fit in the results from the normalization of the relative literatures, and the modified result was obtained using the Bazan's before the models can be found. And after the normalization, the environmental humidity and the strength correlation coefficient can be optimized. The test can be optimized the results of the multiple prediction formulas. And the second stage in the time-dependent behavior will establish similar to the pull-out test. We try to study the interface between the FRP and the self-compact and the seawater and sea sand self-compacting concrete. This is the loading device for the sustaining loads. And after we remove the sustaining load, we can find that the fly ash, because the high volume fly ash will be used for this concrete, the fly ash the fillings can be seen in the pores in the seawater and sea sand self-compacting concrete. And these fillings can be refine the porous structure of the concrete and make the concrete more dense and reduce the permeability and improve the durability of the interfacial bond between the reinforcement and the concrete. And the damage degree of the fiber and the resigned matrix inside the FRP bars is consistent with the degradation degree of the bond strength between the FRP bars and the concrete interface. In those results, we can find that with the increased sustaining low level, the slip amount was increased significantly, and the high temperature also accelerated the interfacial slip due to the sustaining loads. And the use of the seawater and sea sand self-compacting concrete reduces the interfacial slip under the environmental attacks due to the better compactness for these concrete materials. And furthermore, in the time dependence behavior of the FRP and concrete interface under the effects of environmental and sustaining load, it can get some conclusion based on those figures. The higher loading holding level, the larger scoop can be found for the normal the nominal bond retention rate, and the longer load holding time, the smaller scoop can be found. It shows the formation of the crack during the load holding will be reduced the bonding properties of the stress concentration. And the final part of this study, we developed for the concrete beams reinforced by constructed using the seawater and sea sand self-compacting concrete and the GFRP. We try to investigate the long-term deformation. So in the total, due to the time limit, I will speed up my presentation. The long-term deformation of the test of beams is still rapid. The transfer period at the 28 days. The shrinkage of the FRP reinforced concrete beams test is basically consistent with those of the unreinforced concrete beams under the same condition. We can find that in those results, using the high volume fly ash can reduce the mixed bed deformation in some certain. Okay, some results with the fly ash and chloride icon can reduce the shrinkage and the clip of the seawater and sea sand self-compacting concrete. And the initial clip developed the initial significant at the early stage. And compared to the environmental attack, the coupling, the sustained loads and the seawater and seawater environmental can increase the relative slip between the free end of the FRP bars and concrete, and the variation of the trend of the shrinkage strength of the GFRP reinforced seawater and sea sand self-compacting beams is consistent with that of the ordinary beams. And the second further study will try to extend this to some real structures. And I will take about 1 to 2 minutes to introduce our construction practice. Until now, we also developed some construction practice more than around the 32 practical construction, including some bridge deck slabs, some concrete interior layer, and some link slab, some prefabricated structure, and some MIC model. This is one our test with some cooperation between Queen's University. This is bridge built in Northern Ireland. Those 4 panels is for the FRP reinforced self-compacting concrete. This is for steel reinforced one. This is our field test, some configuration for the optical sensors. And this is the arrangement we use due with the consideration of the FRP action action inside the bridge deck. The reinforcement ratio is quite low. It can be seen in those. Even though it's smaller than the steel one, because we consider the action inside. But the applying load is around 3 times of the maximum weight loads in the Europe code, 150 kilonewtons. 150 tons. It can be found that is 400 kilonewtons will be used in the field test, and the recovery is quite good. But this is the most interesting that we can compare the load and deflection of the FRP reinforced bridge decks and the steel reinforced bridge deck. Even though the reinforcement ratio is similar, but the FRP reinforced bridge deck slabs show the similar behavior with the steel reinforced one due to the existing of the action, and this is the total deformation behavior is also very similar, and the strength is very small in this test, and the crack wise is also very small too. This is the result of our structural health monitoring in the real for the truck passing the bridge. We can find that the strength value inside the BFRP reinforcement is very small. It's smaller than 20% of the ultimate strength. And furthermore, also develop a numerical test for the moving loads to study these cracks. It will not be discussed here. And we can find that if we consider the action or compression member action, we can produce the durable economical bridge deck slabs with using the self-compacting concrete and seawater and sea sand self-compacting, the environmental factor can be improved a lot. And the second part for this introduction, we try to build a MIC model in my university. This is some preparation for this construction, the stainless steel and the FRP, and this is construction practice. This is the assembling process for this MIC model, and this is the whole hosting. After that, this model now has been built and used in my university now. Is FRP reinforced seawater and sea sand self-compacting concrete. And after that, we develop LCA analysis. Due to time limit, we will not introduce here. I will make some final conclusions. Well, after the analysis, we can find that we use the GFRP reinforced GFRP reinforced seawater and sea sand slab compared to the steel reinforced ordinary concrete, the carbon footprint can be reduced more than the 20%. And after that, we get some conclusion. The real MIC building was constructed using the seawater and sea sand slab concrete and GFRP, and the fly ash is quite high, and therefore we can reduce the carbon dioxide footprint. And furthermore, you can be after this construction method can reduce the carbon emission compared to the steel reinforced concrete structure with more than 20%. Finally, we make some acknowledgement for some funding to support this research. That's all my presentation tonight. Thank you very much.